So, the obligatory introduction slide. My name is Klaus Iglberger. What I'm doing right now is pretty much what I do for a living nowadays. I talk about C++ in training classes as a consultant. I talk about C++ in a book that I've written, and I do various things at C++ conferences. If you do know me a little, then you know that I'm usually talking about architectural issues. So software architecture, software design, design patterns, design principles. That's what I do, because I just feel it's so important, and definitely the thing that I have to get right before all these little details. But today I actually have a different topic. A topic that I personally feel is even more important nowadays, and a topic that is pretty dear to my heart. And so, right to the point, yes, C++ has a problem. C++ has a safety problem. And I guess this is not new to you. You might have been made aware of various other talks, but also perhaps by publications, for instance, from the NSA. So the NSA, a couple of years ago, very openly proclaimed that C or C++ would be bad for development because of safety concerns. And they very explicitly mentioned that C and C++ would be a bad choice. Today, the words in the newest versions of these articles are definitely much less aggressive. But still, you get the feeling that it would be a bad idea to continue to use C and C++. It wasn't just the NSA, though. Even the White House explicitly stated that safety concerns are very important. Of course, it's about cybersecurity, yes. And C and C++ might not be the best choice anymore. But again, it's not just the US, also the European Union has pretty much similar concerns. They do not explicitly mention C and C++ in that, with that ferocity, but still, you get a feeling that this topic is going to be more important. And if the official governments complain about this so much, then of course journalists get up at this and they complain about C and C++ too, like the internet has a huge C/C++ problem. So, indeed, it sounds like there is a big issue. So, C++ has a safety problem. Does it really? Well, just to give a short answer at this point already, yes, absolutely. But, and here's the big but, only if you're still trapped in this classic C++ mindset. And this is exactly what I want to dwell a little bit on. But first, how did you get there? Why do we actually talk about this today with heated discussions, many talks, etc.? Well, if you know C++ a little bit better, then you know that pretty much whenever we make a decision about the language, we primarily choose performance. Performance is important because, of course, it's about money, it's about energy. Performance is important. So with very few exceptions, we always choose performance. So when I say exceptions, perhaps you know that a std function might not be one of the greatest performance choices, but still, performance usually is top most important. But it's not just random, there's a reason. And that is that safe can be built on top of fast. And this is something John Culp expressed in his talk pretty nicely, and so I just repeat his words because I actually believe they're quite accurate. This leads us to this observation that you can build safe on top of fast, but you can't build fast on top of safe. What this means is that, given an API that does no domain or other testing, one can build an interface on top of that API that adds any necessary checking, making it safe. And so from this perspective, it's actually quite reasonable. Yes, so you're fast and safe at the same time, which actually makes a lot of sense. And you can choose whatever you prefer, maximum performance, or perhaps a little safer. However, at this point, I should point out quite clearly that there's a misconception to some extent. Many people believe that because we're using C++, the code is fast. Okay, no, I do not believe that. So, quoting Chandler Carruth, C++ doesn't give you performance, it gives you control over performance. So, keep this in mind because I actually believe this is quite important. So, it's not automatic, not everything is just happening magically. We have to do something. We are the experts. So we should use this control. But now, was it bad that we actually chose performance whenever we could? Does this now mean that because of these choices, C++ is broken? Well, at this point I can again clearly say absolutely not. No, absolutely not. But we have to do some things. So we first have to do some work in regard of making the language a little safer, step by step. And so we should actually invest some work in order to make it much simpler to write the safe thing by default. Yes, I believe this is absolutely necessary and absolutely important. But then, here's my personal opinion, there's actually something that's even far more important. Something that I'm most concerned about and which I consider to be the real problem. I think that we have to communicate so much better how to actually program C++ today. Because, my opinion, we actually have all the solutions. We have them, we just don't use them. So, to quote Herb Sutter from one of his longer articles, the immediate problem is that it's too easy by default to write security and safety vulnerabilities in C++. That would have been caught by strict enforcement of known rules for type, bounds, initialization, and lifetime safety. Known rules. Known rules, indeed. For decades, we know how to use the language properly. And so, let's take a look at these known rules, few of them, not all of them, for bounds, type, initialization, lifetime safety. So let's take a look at the 4 riders of the apocalypse. So, and know what? I also throw in a 5th one. A 5th rider, let's throw in undefined behavior as well. Okay, now you smile and say, Klaus, and here goes your nice big figure of these 4 riders of the apocalypse. But I actually do not think that it's just 4 nowadays. It might be 5. And so my figure of speech actually holds. I can really talk about the riders of the apocalypse. And so let's start with bound safety. All right, so let's jump into code. An example, a simple example. Let's talk about countries. So here's a struct country, and every country has a name, a capital, which are represented by a string, has an area in square kilometers, and a number of residents, represented by a float, so it's the number of residents in millions. Okay, it's a simple struct, the rest of the code is totally irrelevant. Then we have a continent. A continent has a name, and additionally, a vector of countries. So all the countries on this continent. So, but now the real thing, a function called print 5 biggest countries. So we start this function by creating a vector of continents. This may be the return of some function that just gives us all these contents with countries. And now we have these continents. Good. Then we create an empty vector of countries and run a nested set of for loops. So in a training class, I would now ask you, what does this do? So I need to look at this code. You'd look a little closer. You look again, think deeper. And then after 30 seconds, 40 seconds, perhaps a minute, somebody makes a first guess at, we fill countries into this vector. Okay, correct. I mean, it's a vector of countries, sure, but how do we fill the countries into this vector? Okay, then again, code is scanned even more. Okay, we order them. Correct, but how? Oh, and then it actually takes even more seconds. Or somebody just guesses because it's a 50-50 chance. So we put all the countries in by descending area. So the largest, the biggest countries first, the smallest is last. Good, so now we have this vector of countries sorted by area. And now we actually take the 5 biggest countries, biggest by area. And then we run another set of for loops. And again, I would ask, what does this do? People would look at their code. We try to understand what it's doing. And it feels a little convoluted, it feels a little complicated. But again, after, say, half a minute, somebody says, we are reordering by the number of residents. correct. But how? And then 30 more seconds pass, and then somebody crucially says, descending? Correct. So now we have the 5 biggest countries, but ordered by the number of residents. Most populated country first, least populated last. So, and then these 5 countries are printed, say by cout. Good. So, now we know what this function does. But how long did it take us to understand what it is doing? Is this something that we have guessed at first glance? If you can, I'm deeply impressed, but I actually believe no. I also would have taken 5 minutes to really understand what this is doing and having the confidence to know what this is doing, not just a wild guess. This is complicated code. But there's something even worse. And you might have spotted this. +5, less than 4, less than 5. There's an implicit assumption in this code. An assumption that means, well, there's at least 5 countries. Oh. So implicitly, this means that we have undefined behavior in this function. And just for reference, this is now for today the undefined behavior emoji, right? So whenever we see that, there's a problem. So we need at least 5 countries for this code to work properly. Now, of course, the first reaction is, oh Klaus, we could add an assert, then this could not happen. Okay, good, it's a mean to get to something, but I believe still this is just bad code. We didn't even see that there's undefined behavior on the first glance because it's so convoluted, it's so complicated. So, we can do better. This just is not how we write code today anymore. No, today we would do this. So again, it's the same function, print 5 biggest countries, but first, it now fits in one slide, easily. It's much shorter. Again, we start by getting all the continents with countries, same function call, same vector, but now we actually work with this vector a little differently. So we take the continents and we pipe this continents into an algorithm, to transform, and we transform to countries. Oh, nice. So no more for loop, but a direct use of an algorithm. And yeah, there's no pipe operator. It's a bitwise OR that we misuse, but it's nice. It feels like we concatenate these algorithms. Then we join all of these little vectors of countries into one imaginary big vector of countries. Good. So now we have this big vector. It's not really a vector yet. It's a view. And so we now put this into real vector. So to a vector. So it's all the countries, but they're not ordered in any way, so we now sort the countries by area. Nice. So you don't have to guess what this is doing. It says so right away. It's a sort. And at the same time, actually increased performance quite considerably. Yes, because before we actually used an insertion sort, that now we use an intersort. And not just this algorithmically so much more efficient. Okay, you could complain that at maximum there's probably 200 countries if we consider what we have on the world, and for 200 countries it's probably not making a big difference, but still, it's better code, it's faster and simpler. So now, we have all the countries, but now we just need the first 5. Okay, so now we take the first 5 countries. So, but at this point, you could now complain and say, "Why, Klaus, there it is again, the 5, undefined behavior." But no, this always works, because take takes at maximum 5. If there are 3 countries only, then it takes 3. If there are 4, it takes 4. And when you have at least 5, it takes 5 countries. It always works, unconditionally, which is amazing. But at second, it doesn't create a stood vector. It creates a view again. A view that doesn't have to allocate, doesn't have to create an object. So it's again faster, it's cheaper. And this view can be sorted. So we not directly sort in the big vector the first 5 countries by population, and then print this again. Do you see the difference? It's so much better, right? This is how I want code to look today. This is the ranges style. And yes, it's much shorter. Obviously, I didn't have to scroll anywhere. It's small. It's simpler. Simpler to write, but also at the same time so much simpler to read. And this is what code most often is. We read this most often, and I believe if a colleague of mine sees this, it's reasonably easy to figure out what this is doing, but just following the names. Good. It's faster, which I mentioned on the way, which everybody loves. Fast is good. But then, most importantly, there's no manual use of indices, of iterators anywhere. And so suddenly, it's truly impossible to have an out-of-bounds problem. This code works for any number of countries. This is how C++ looks today. This is what we do. This is what we should do by default. This is it today. And yes, it's perfectly aligned with C++ philosophy. We built safe on top of fast. This is it. This is what we should do. So, I hope that you realize this is not news. Oh no, so many people before me have talked about this. So many people like, for instance, Jean Parent in 2013. So Jean, at this conference in 2013, made a statement that I believe really makes a huge difference. And so I'm just going to repeat that, because I believe that the words were just good. If you want to improve code quality in your organization, I would say, take all your coding guidelines and replace them with the one goal. That's how important I think this one goal is. No raw loops. This will make the biggest change in code quality within your organization. The biggest change in code quality. So at the time, perhaps this was a little provocative. But I think today we've understood that he was so right. Yes, that's it. The style, the difference. That's so much better code. But I should point one thing out. Many people always feel like, oh, he says we should not use any loops. No raw loops. And this doesn't work. No. Even then, in 2013, Jean did not say that you should not write loops. Absolutely not. And this is explicitly mentioned in the talk. He explicitly says it's about the simple code. So if you have a for loop that is so simple that everybody can understand it by just looking at it, that's okay. That's perfectly fine. It's not about not using loops. It's about writing the simple code, the most understandable piece of code. And that already, as I said before, in 2013. But now, let's be honest. 2013 is also kind of late. This philosophy, this style of programming has been introduced in 1994. This is when the STL was merged into the C++ standard library. And since then, we just have this philosophy. No raw loops. And so it's a little surprising that we still talk about bound safety issues. Why? So, safety takeaway number one, no raw loops. Okay, but of course, I do training classes, I tell this to people, and people complain. They constantly complain. It's so complicated. I would like to use it, but my colleagues wouldn't understand my code anymore. This will probably reduce performance, right? And of course also, I'll rather stick to what I've used the last 20 years. Sounds familiar, doesn't it? It kind of does. And it's hard if somebody kind of doesn't feel that it's better. So how do you convince someone? However, there's also the ultimate argument for people that just don't use C+20 yet. Oh, I cannot use C+20 yet. Thus I cannot use ranges, so I'm good. No. So, if you hear this, don't let it count. You can use ranges in any standard. And so, for instance, you could use the original library, ranges v3, as a replacement for std ranges if you wanted to. And note, here, you can use this in C+14, 17, 20, and of course, ongoing. So this library is most likely available to you. But then still, some people complain, because in recent years, we have actually seen a lot of complaints about the ranges implementation. I've heard that C+20 ranges don't work so well. Okay, and there's some truth to that, some truth, but of course, it's not like everything is broken. there's a couple of flaws, and there's a couple of pitfalls. But ultimately, if you use this in a simple way, the code gets better. It's simpler. And so, if you don't like the ranges for that, standard ranges for that reason, just use another library. For instance, I would recommend the Flux library from Tristan and Brindle, which is a little different. It feels a little different, but it, for instance, avoids the problems of standard ranges. And it's fast. It's really fast. And so from that perspective, me, but also Tristan himself, I would say, it doesn't matter which kind of ranges you use, but you should use ranges. So ultimately, it's not a language problem. It's a mindset problem. It's a people problem. And no matter what the problem is, it's always a people problem. Okay, so let's talk about the second writer. Let's talk about undefined behavior. So again, let's jump into code. This time I have a generate prices function. So generate prices takes a start price, takes a number of prices that I want to generate, and it returns a vector of doubles. Yeah, these doubles are the generated prices. Okay. So we start to create a vector of doubles with the according number of elements. Put the start price right in the beginning at index 0. So then we compute a next price. Somehow the logic is totally irrelevant, before actually generating all the prices from index 1 to the end. Okay. So, and we return the prices. Then, of course, what you should do is we should test. We should test this function, so test generate prices. The function takes a start price, takes the number of prices we need, but also the expected prices. So that we now can create two vectors, the one generated by generate prices, then an expected vector, and we can compare them. Is the result what we would expect? Good. And of course, we use an algorithm for this purpose. And then we could assert. We could test the generate prices function, so we can call this for 0, for 1, for any number of prices. Good. I believe this time actually expected something. And so some of you now might have actually seen that, again, there is a problem. What if the given number of prices, the count is 0? Yes, again, index 0 plus 1. This will not work. This is undefined behavior. Okay, so now you not say, okay, Klaus, but isn't this a bounce problem again? Okay, correct. But this time, we're actually going to address this a little differently. So let's do the following. So, again, we can do better. Let's actually use a keyword. A keyword from C++11. Let's use constexpr. So let's make the general prices function constexpr. And why not? It's a simple keyword. There's nothing that would speak against that. So now you might argue, okay, now we can do some price computation at compile time. Well, what's the point? Okay, it just works, right? So then the test general prices function, let's make this const eval. Not because I have to, just because I can, and I can show this keyword too. So this function now must be used at compile time. Okay. And since we have to use it at compile time, the assert in the main function is not going to work anymore. So let's turn this into, yes, of course, static assert. Something beautiful is going to happen. And this is probably the best part of this entire talk, so cherish it. This code is not going to compile. Compilation error, which looks like so many compilation errors, not particularly simple, I know. The first sentences make a lot of sense. Error, non-constant condition for static assertion. Okay, what? However, look at this line. Dereferencing a null pointer. Whoa! The compiler realizes that we're actually trying to access the 0th element, so index 0, of an empty vector. Understood vector probably has a null point inside. So, undefined behavior. And the compiler flags this with a reasonable error message. Amazing, isn't it? Breathtaking. Because this cannot happen. We cannot have this undefined behavior in the code. And it's not just GCC. No. Clang, pretty much just the same thing. Slightly different in the message. Again, static assertion expression is not an integral constant expression. Note, assignment to dereferenced null pointer is not allowed in a constant expression. Yes, not allowed in a constant expression. And this is not a coincidence. This must happen. This is exactly what the C++ standard says explicitly in this class. So I just read the last sentence. Evaluation of a constant expression never exhibits a behavior explicitly specified as undefined in, and it gives two references, which pretty much is the beginning and the end of the C++ standard. So everything in the C++ standard is marked as undefined behavior cannot happen in a constant expression, constexpr. Beautiful, isn't it? Beautiful. Because this means that there is no undefined behavior if you just use the language as it is supposed to be used. Yes. But then again, it's not new stuff, new info. There's at least one person in the community who has been talking about this, it almost feels like a decade. So this is not from many years ago, was just last year, but at NEC Tech-Town, Jason Turner gave us this pro tip. Make sure you test in both constexpr and non-constexpr context, which nowadays, by the way, works automatically if you just use the according test framework. So, but he has been given this advice, indeed, for years. 2017, together with Ben Dean, he talked about constexpr all the things. And note the all, it's in capital letters, because this is the message. And it's not about, let's do every computation at compile time. It's of course also about, there cannot be any undefined behavior. We can test at compile time. And it's just so good. And so this is what we do today. We constexprify the things. Now, if you think that, okay, there's limitations because the standard library itself is not fully constexpr yet, true. Depends on the standard, but people like, for instance, Hanna Dösikova have been working on this for years now. And hopefully now, in C++26, almost the entire standard library will be constexpr. And so then really there is no excuse anymore to not constexpr everything. And so, safety takeaway number 2, constexpr all the things. So, I hope you not agree. But then, of course, again, there's people that complain. I cannot add constexpr in front of every function. So much of our functionality is not constexpr yet. And a compiler would constantly complain. Okay, potentially true, absolutely. But it's not that you cannot go there. So from my personal point of view, it's just a matter of design. It's a matter of structure of the code. If you structure your code such that, say, 90% of the code is in constexpr functionality, and the remaining 10% is harmless, then you're actually on at a good point. And how this can work is something Brian Ruth has nicely demonstrated in thinking functionally in C++. So he just explicitly separates actions, calculations, and data. If you do this consciously, then, well, indeed, 90% at least of the code is suddenly green. Can be constexprified, works perfectly. And just a few things, other things might not work yet. Yeah, like cout, etc. Good. So this is, I believe, a very, very simple, reasonable way forward. So it's a mindset problem. It's a people problem. And no matter what the problem is, it's always a people problem. Okay. So let's take a look at the third rider, type safety. So now again, of course, I have a code example, but I apologize up front. Guess what I'm not going to show you? It's the worst piece of code that I've probably ever shown on any slide. It really is. And so if this makes you feel sick a little bit, don't take it out of me, please. Yeah, I'm just a messenger here. So we have a function that I call extrapolate position. That's the best part of the function, by the way. Then it goes downhill. So this function takes two double references, x and y, which I can kind of think is the position. Okay. Then it takes a double t, time probably. Then it takes two more doubles, vx and vy. That's probably velocity in 2 dimensions. And then an acceleration, ax and ay, both defaulted to zeros. So if you now feel a little sick here, I totally understand. Me too. Yeah, I really don't like this. If you do feel like, okay, that's what my code looks like, okay, then I have work to do. Because this is just not good. It really is not. It's so easy to swap values. So easy. So why is t, again, probably the time, the third parameter, is this intuitive? Is this what we would expect? Oh, absolutely not. It's kind of random. So we could forget about this or expect it's the fifth one, so we could swap values. More than 5 parameters. Okay, that's subjective, but indeed, some people feel like more than 5 is hard to remember, so we'd have to look up some documentation every time we try to call a function. And if you look at this, these calls here, is it clear what this does? These many values, bad code, hard to understand. Then, which units are used? So for the time, for instance, is this in seconds, minutes, hours? We have no clue. And again, we would have to look up the documentation, which hopefully explains what is expected here. And returning via mutable references? Seriously? Just because it's 2 values? It's absolutely terrible. So this is absolutely bad code. It really is. And this is definitely not up-to-date C++. But again, I would not argue this was ever up-to-date. This was never good. Since the very beginning of the language, since 98, even before that, we use strong types to solve this issue. So instead of taking doubles, we use types that actually express what is expected. So, for instance, first parameter is a position. Now it's clear. It's not just x and y, and we have to guess, but now we have an idea what this is. Then second, the time is in seconds. And it's in the type system. It's not just documentation. Good. Meter per second. Meter per square second. It's documented in the code. Self-documenting code. And at the same time, it's now absolutely impossible to actually swap values. You cannot give a second where position is needed or a second where meter per second is required. This is absolutely easy to use. And here, if you read this, we actually believe this is so much easier to understand too. Absolutely, because in the code you already see which is which. So much better. So, what is a strong type? Just as a quick example, because it's actually really simple. It's a class that encapsulates the thing that we need. So double, for instance. And it's a type that can, of course, encapsulate a lot of safety. For instance, with explicit, an explicit constructor. This is a must-have for a strong type. Yes, of course, you realize that that's one of these unfortunate defaults that we have in the language. Every constructor should be explicit by default, but it's not yet. Hopefully you can change this one day. But then constexpr, everywhere. Why not? It's a wrapper around a double, so why shouldn't I do this? And no discard. Yeah, true. It's a tiny addition, but yet it again adds a little bit of safety, which I could not do if I have just a double. Nice. So if I use this, I could now create seconds by just passing doubles. Now I can express that this double is not just a double. It's a second. It has a meaning. It represents something. But what if I do not pass a 42.0, but a 42? Does this compile? Oh, absolutely. Absolutely. If you're thinking that explicit will save us for this kind of misuse, no. We explicitly call a constructor. We just passed the wrong type. But unfortunately, there's a built-in conversion. Int can be converted to double. The compiler just tries to help us, help in quotes, and converts the integer to double implicitly. Also one of these defaults we really don't like anymore. Implicit conversions of fundamental types. There really is no way to control them, right? Oh, but there is. And it's so simple, seriously. So let's just update this by 2 additional lines of code. One for the constructor, one for the assignment operator. And so the constructor, we just make it a function template. So we now take a u. But then we now don't take any u. No. We require explicitly that this u is double. So same as u double. You see what this means? Yes. Suddenly it's absolutely impossible that somebody gives you something else than a double. Users now are required to give you a double. They cannot pass int, they cannot pass float, not even float. They have to give you a double. So one additional line of code, this height safety problem is absolutely resolved. And of course, I would do exactly the same for the assignment operator. We just require that the given value is a double. Yes, you are in control. You can say that this is what should be. But if you now feel like, whoa, that's really strict, all I want is to prevent the bad conversions, the narrowing conversions. Okay, fine, so you can do this. So you can use your own requirement, your own concept, for instance, no narrowing conversion, u double, and well, perhaps float is okay, perhaps int is not. You decide. You decide because you are in control. And that is, again, philosophy of C++. So C++ doesn't give you safety, it gives you control over safety. It's not there by default. But if you want to, you can get all the safety you want. So, safety takeaway number 3. Use strong types. Even for the little things, absolutely. It's simple and very, very easy to make the necessary kinds of changes. But know what? Even something that seems to be obvious, people complain. And this time, of course, about the big thing. What about performance? Aren't abstractions slow? And really, this is what most people are worried about when using strong types. Doesn't this have an effect on the assembly code? So, this is something that we could do an entire talk on, but quick demonstration. So here on the left, I now have 2 functions called test. One takes an int, and the second one takes a second, which is just coming from a more generic strong type. So it's pretty much exactly what I've shown before, slightly extended. So what do you think? Which of these 2 test functions is faster? Correct. Both are exactly the same. Both, for both, the compiler just issues a single assembly instruction, a load effective address, which means we just add something. So it doesn't matter which of these 2 versions you use from a performance point of view, but it very much matters from a safety perspective. The second is just so much better because you expect exactly what you need. So much better. And so again, this is just what we do. We build safe on top of fast. We always have. And for this particular case, Guy Davidson actually called this the true superpower of C++, abstractions. This is what we do and what we have done since the beginning of computation. We want more about this, want more of this. Does this mean that I have to write all of this stuff myself? No. That I believe, yeah, that would be a problem. But this work has been done for you already so many times. There's so many libraries that actually help you. So seconds, for instance. Oh, you do not have to write a second class anymore. It's already in the standard library. Chrono, since C++11. But if you need anything else, like meters, like becquerel, newtons, whatever, well, use a library. One that I would recommend is Björn Fahler's strong type library. It's free to use, it's on GitHub, and it's neat, it's little, it doesn't add a lot of dependencies. Good. If you don't like this one, there are others. Jonathan Müller has written TypeSaved, which is a little different, but pretty much just the same job. It helps you to express what you really want in code. But there's perhaps one more that I definitely should recommend, because this actually might change the C++ standard in the future. And I'm talking about the MP-Units library from Atush Push. So this library is actually headed towards standardization. Not C+26, no. That would be great news. But we are aiming for 29, which is totally realistic. And if you take a look at this library, you will realize, wow, this is beautiful. This is powerful. It allows you to really express what you want, and at the same time, it allows you to make your code so much safer. And it's fast also, absolutely. Yeah, Matush makes make sure about this. So check this out. I believe this is going to be the future of strong types. But still, it's so much more complicated. Okay, people complain. They will always complain. But my personal opinion, some people prefer to search for program errors for a few days instead of spending a few seconds to add a helpful line of code. Okay, will always be this way probably. So, it's a mindset problem. It's a people problem. All right, there's one more writer, lifetime safety. So now for this, I actually go into what I usually do. I talk about design patterns. So I now go to this book. Yeah, no, and for some it brings back bad memories, some bad dreams perhaps too. For others, well, it's the reference on design patterns, The Gang of Four book. Released in December 1994, which actually means this is ancient. Yeah, from a computing perspective, this is ancient. But no. This is not outdated. Okay. The code examples they're pre-C++, pre-standard C++, but these patterns are used everywhere. And even if you're not aware of them, you use them every single day, everywhere, all over your code base. And the standard library has thousands of these patterns inside. Thousands. And I'm not kidding. So, this book is the source of 23 of the most commonly used design patterns. This is why it is still so commonly used. And yes, 1994. At that time, everything was object-oriented programming. Yeah. So it's not to blame on these guys. It just was the time. So 1 year after this book, so 1995, Java was released, which kind of shows you, oh yeah, this is when everybody thought that everything is an object and you have to inherit from an object. It was the time. But this time brought about design patterns based on inheritance. So I've now picked one of them, the so-called visitor design pattern. Now, today I'm not going to bore you with design patterns. I will not explain this. It's just that we see one of these human class diagrams. And that we see that, yeah, it doesn't look simple. It doesn't look trivial. And it actually brings about a lot of problems, a lot of disadvantages. So first, you might realize that there are two inheritance hierarchies, one on the left, one on the right, which, of course, consequently brings along a lot of virtual function calls. So, and virtual functions, unfortunately, are more expensive than regular functions, or even inline functions. And so performance is most definitely reduced. Double dispatch. Yeah? There's no way the compiler can help you here. Absolutely not. Then, of course, this style of programming promotes dynamic memory allocation. Doesn't have to happen, yes, but very often reduces, make unique, for instance. But the memory allocation itself already is slow. Yeah, every call to new, every system call is something that drops performance. And now, of course, it depends on how you use this. And do all the allocations up front and then just use stuff. It's not as bad, but if you very frequently create things, that's a performance issue. Then, of course, these pointers require us to manage the lifetime. Unique pointers, smart pointers in general. Good. So we cannot miss this. We cannot forget to delete. Great. But even though we cherish these smart pointers, they're still just pointers. Just pointers. And so It's just an address, a runtime address that, again, doesn't help the compiler, so it helps to reduce performance. It contributes to that. It's an indirection. And probably worst of all of that, it's still pointers. Even unique pointers, even share pointers can be null pointers. And it actually is possible very much to introduce lifetime-related bugs. So, and that probably is the biggest problem of all of them. So now, pointers, references too. This is something that Dave Abrams has been talking about also for years, decades probably. He then went to Apple, helped to develop the Swift programming language, and he tried to stick to values most of the time. But now he's back in C++, again, talking about why values would make things better. So in this talk, he actually explains this in a lot of details, really good recommendation. But I just used the first words he used in this talk, just the first 2-3 sentences. People, we have a problem. And it's one we may not really like to face. In fact, we maybe can't even see it because we are swimming in it. It's like water to the fish. I'm talking about reference semantics. So he talks about this problem, why pointers and references make the life so much more difficult, why reasoning about the code is becoming so much more difficult. And his answer, an answer that maybe other people have given as well, is to prefer values, value semantics. So now I just want to give an example. And I'm using the design pattern that we've just seen before, the visitor design pattern, and I just show how this would look today in modern C++. So we start with a circle class. Okay, it's a benign circle. There's nothing special. It has a radius, there's a couple of other data members. It's a circle. But the most important, the most interesting thing is what you do not see. So there's no base class. Good. That's an advantage. Indeed, from a design perspective, you can take any circle out there, any third-party library, because not requiring a base class, a specific one, is non-intrusive. And I will not use the circle as a pointer, or via pointer, but as a value. Nice. So it's simple code. Of course, we have many other shapes as well. Say there's another square, and imagine there are 10 more, same idea. Then some operations, say we want to draw them. Again, this is simple code. But again, it's most important what you do not see. Again, there's no base class. There's no virtual function. There's no pointer. And no, we're not going to use this by pointer, but it's a value. And how? Well, we're going to use C+17 variant. So this variant now is our abstraction of the different kinds of shapes. So this variant stores a circle, or a square, or rectangle, ellipse, whatever kind of shapes you have. And this is a value. It's not a pointer. It's not managed on a heap. It's a value only, which we use as a value. So this function here takes a vector of shape values, not shape pointers, base pointers, whatever. It's values. And we simply visit with a draw function. Not draw function, the draw function object. Simple. But the best part is the main function. Oh, absolutely. I love that. So the main function starts with an empty vector, and then first adds a couple of shapes. A circle, a square, say another circle. And we draw them all. It's simple, isn't it? It's really simple. Now, to prove that it's simple, try the following. So first, okay, the name and place back is not a great function name. Okay, replace this with add. Cheating a little bit, I know, but okay, replace this with add. And then show this main function to somebody who's not involved in any kind of programming. Show this to beloved ones at home, to your husband, to your wife, if they don't know programming. And ask them, what does this code do? They know. They can explain to you that, there are some shapes and you add a circle. Then you add a square. Then you add a circle. Of course they know. It's so simple that even people that do not know programming, are not in this profession, understand this piece of code. That's what we need. This is what we need. This is good code. And this is exactly what this reference semantics gives us. Simpler, more expressive code. So, value semantics. No base classes anywhere, no virtual functions, no pointers in the entire example, no memory allocations on our side. StdVector still allocates internally, but we don't really care about that here because we don't manage it. We don't have to do this. It's so much simpler, and at the same time also, again, so much faster. So in comparison to the classic one, this is probably 2 to 3 times as fast, which I cannot explain here in detail, but I've talked about this in 2022. So this entire talk about the visitor pattern, performance results, other forms. So if this is interesting, check this out. But also make sure that you also check out the other value semantics talks I've given, for instance, about type erasure, which is at the other end of the design spectrum. So kind of augments the visitor talk. So safety takeaway number 4, prefer value semantics. So I hope that you agree by now. This is truly better. It's simpler, it's even faster. Why isn't everybody using this? It's a mindset problem. It's a people problem. So, okay, yeah, hopefully at this point, you agree. I get it. The language might not be perfect. For instance, all the defaults are wrong, unfortunately. And we still have to do some homework to fix those things. But it provides good solutions. It's not really a language problem. I don't believe it is. Yes, of course, programming in C++ is not safe by default. But we are in total control of safety. In total control. So we can use our solutions to pretty much eliminate all of these safety issues. So if you use algorithms and ranges consciously everywhere, then more than 95% of all possible bound safety issues are gone. Then if you use strong types everywhere, which it should anyway, that's how we program in C++, then 99% of type safety problems are gone. Okay, and I say 99 because if I would say 100, you would later write bad emails to me if you still encounter a problem. So this is safe for me. But I believe pretty much all of the type safety issues are gone. Then almost all lifetime safety issues are gone. Again, 99% by just using values, preferring values. And if you just use constexpr, potentially some tools like sanitizer, also, there is no undefined behavior anymore. Yes, this is not new solutions. Absolutely not. And some of them have been around for a long time. 1994, that's how long we've been using these algorithms, hopefully. So the real problem, it's a mindset problem. It's a people problem. So I think by now you have an idea what I consider the real problem. But now let's talk about people a little bit. So first, I would say, sure, of course, that's just people that don't know. Of course. Some people still write a lot of what I would call classic C++. They write their own for loops, they just pass doubles and integers en masse in function APIs. So they don't really work according to our best practices and guidelines. And I also don't use the tools. Testing frameworks, sanitizers, static code analysis. Unfortunately, still too many do not do that, although it should be an integral part of every project. So, but at latest at this point, I believe some of you are glaring really angrily at me and say, Klaus, no, we do use these guidelines. We do use all of that. We do use C++ as it should be used today and use all the tools. I know. So that's the unfortunate part of this talk, because quite honestly, I can talk about this for an hour to the wrong people. Because I know you use this stuff. Yes, you are exceptional. And I truly mean this. Truly mean this. You go to conferences like this to actually learn about how to use the language today. You go to a conference. You might actually also go to user group meetings somewhere close to your city, if possible. You might be one of these few people that actually once in a while pick up a C++ book, that read blogs on the web, that actually follow discussions on Reddit, perhaps even on LinkedIn, social media. Yes. And truly, this makes you exceptional. I think this makes you part of this little bubble in the center of the community. And I would call this the 10% bubble. So now why 10%? Well, do the following, just for fun. Go to YouTube and look for one of Björn's keynote talks at CPBCon. And interestingly, this is the talks that get the most views. For instance, 2024, the keynote talk from Björn Strustrup got approximately 180,000 views. Well, now you think, whoa, 180,000 views, that's amazing. I wish my talk would get so many views. Oh yeah, I do too. But then wait, 180,000. How much C++ developers do we have in the community? Well, actually, it's a couple of millions. So let's roughly say 10 millions. And so if you have this number in mind, then actually 180,000 is almost nothing. It's ridiculous. And so once in a while, actually, do not just talk about the 10% bubble. Sometimes I'm pessimistic and talk about the 1% bubble. And yes, this is the bubble you're in. You do the right stuff. But this, once again, makes you exceptional, unfortunately. So, yeah. This looks like fun, but actually it's sad. Okay. So isn't that now a strong argument to just use another programming language? If so many people just don't know how to do things properly, isn't this an argument to do something else, better perhaps? Well, of course you can have different opinion, but my opinion is that it's just so much more expensive and more time consuming. So some people prefer to learn a new programming language for several years instead of just spending a few weeks to probably learn their own programming language. Okay, this may be my personal opinion, but, well, you may have your own. So then, some people don't know, but unfortunately still speak up. And that actually is, from my perspective, one of the biggest issues today. And so, yes, of course, I'm talking about social media. I'm talking about discussions where people give their opinion, sometimes even with strong words, but you, as somebody who knows, actually realizes quickly that this is total bullshit. And yes, I know, that was a bad word. But it is true. Some people speak up without having any idea of what they're talking about. So to give an example, in a couple of weeks ago, perhaps 2 months ago, actually on LinkedIn, saw somebody who openly proclaimed that people should use Rust because Rust is a standard and C++ does not. Ridiculous, isn't it? Yes, of course, you can write comments like, oh, this is total lie, false information, but still, this is the people that speak up on social media. So this is incompetent people, plain and simple. But for some reason, apparently it is still okay for them to spread this misinformation, perhaps because ignorance is bliss. I believe this is one of the biggest problems of our time. But yeah, okay. Let's dwell on the other kinds of people. Because some people actually would like to know. Yes, if you come into the language as a beginner, you want to know how things work. You want to learn the good way of doing things. And we have a lot of books for that. Just mentioning books. Perhaps because I love books, and this is a nice slide because it's very colorful. Many, many books that really teach how the language works. So, let me tell you a little war story of mine. So I was doing a book review on one of the books that was updated to C++23. And in chapter 7, when I read this, it actually blew my mind. In many ways, programming C++ is like driving without a road. What? In chapter 7 of a beginner's book? Seriously? this is how we really want to teach C++, to give people a bad feeling about it right in the beginning? Oh, absolutely not. This is also absolutely ridiculous and not acceptable. And so, I tried to do my best and I spoke up. I wrote a review and said the following, in, I hope, really reasonably nice words. This paragraph sounds like it's a very bad idea to use C++, and that in chapter 7 already. This kind of thinking is the reason why C++ is considered an unsafe programming language. I would strongly recommend to change the order of chapters. I would first teach the safe/right way, then how the stuff works under the hood. As we people start to learn how we use C++ today, not how we used it in the 90s and 2000s. I think this is a good argument, right? It makes sense. Start with the safe stuff and then later teach people how things work under the hood. But know what? Yes, exactly. I was removed from the review. Yes. And why? Because it would have been too expensive. And oh, this is not possible. Money and other arguments are more important than doing things right. And I don't believe that this is good. So, if you ever read such a book, just give a very bad review on, say, Amazon, because many people read that. Review it anywhere negatively. Seriously, this is not acceptable anymore. So, to give good examples, personal preferences, but still, I would recommend these two books nowadays. So I would first recommend the right book called Learn C++ by Example from Frances Buentempo. This is a good book because in this book she actually really shows how the language works today. She does an update for people that knew C++ a long time ago but now need to know about 11, 14, 17, etc. And it's fun too because she uses little games, fun games like Word Smash, etc. that make it fun to read and to experience. Good. It's not a beginner's book, though. And so I asked Frances to write a beginner's book in the same style. And I was so lucky that she actually said yes. She still hates me because of this, because it was extra work. But I think it actually is good for the community. And that's the left one, Introducing C++. It's not finished yet. I believe it will probably hit the shelves in early 2026. I hope so. But again, this book shows how C++ is used today. You don't write for loops, you use algorithms. And still she shows how the for loop looks like. But the simple ones, the ones that don't break anything, that's how the language should be used today and should be taught today. So it's a mindset problem. Absolutely. So what can we do? We, the people in the 1% bubble. Well, quite honestly, I can do my part. So I, as a trainer consultant, can just tell people what should be, how this should work, what they should write in code. That's my part. And I try to do the best I can. But quite honestly, I don't think that's enough. I don't think so. Because I cannot teach millions of people a year. I would be happy if that would be possible, but no, unfortunately not. This actually means I need you. You, the people in this 1% bubble. You know how things should work. You have a feeling. You know what is good and what works well. So spread the word. Talk to your colleagues. Talk to the people in user groups. Talk to the people how things work. So tell them, spread the word that working in classic C++ is like groveling in the dirt. It doesn't feel well. And tell them that they should stand up. Tell them to clean up, to become proud C++ developers that know about the best practices and use their coding tools. And hopefully, over time, this makes a difference. So, because if that would happen, if people would wake up and do the right thing, then with our best practices and tools, we could easily remove the vast majority of safety issues. And if that would happen, then, in the words of Herb Sutter, if there were 90 to 98% fewer C++ type, bounds, initialization, and lifetime vulnerabilities, we wouldn't be having this discussion. Thank you very much.